Hello everyone and welcome back to our engineering learning series. In today's session, we are going to explore one of the most fundamental concepts in electrical circuit analysis. It's Kirchhoff's law. Whether you are a beginner in electrical engineering or preparing for advanced circuit analysis, mastering in this Kirchhoff's law is essential because they form the backbone for solving complex circuits. So let's dive in it. Before we move into Kirchhoff's law, let us quickly recall some essential definitions. Right. So what is a node, right? And what is a branch and what is a loop? Fine. So a node, a point where two or more circuit elements connected. Every node has a specific voltage with respect to ground. Branch is a single circuit element like a resistor, source or capacitor connecting two nodes. A closed loop path in a circuit starting and ending at the same node without crossing any element more than once. For example, in the circuit with a voltage source, a current source, and the three resistors can be identified as three nodes, five branches, and three loops. Recognizing this is the first step before applying Kirchhoff's law. Now let's talk about Kirchhoff's law. Or KCL, Kirchhoff's current law, can be termed as KCL. Uh, the definition of it's like the algebraic sum of current entering a node is equal to the algebraic sum of current leaving the node. To put in simple words, a node doesn't store charge. What flows in must flow out. Mathematically, we can tell sum of incoming current is equal to sum of outgoing current. Right. So, in order to apply this to a circuit, assume that we have a following circuit, right, which has a node A with the current I1 in the node A as it enters, and then that another branch we have current as another two nodes I2 and I3 are leaving. So that according to KCL, current entering is I1, current leaving is I2 and I3. So as per the statement, current entering is equal to current leaving, so that I1 is equal to I2 plus I3. This law is widely used to set up the equations in nodal analysis, which is a systematic method to analyze the circuits. To take a close look into the circuit, on left we have a voltage source VSB, I mean Vs, which is represented as source voltage connected to a resistor R1. In the middle, we see two resistors R2 and R3, each connected vertically down to the ground. On right, we have current source IS delivering current upward, and across it, we measure the voltage V0, I mean the output voltage. Now, if you observe carefully, the circuit has three distinct nodes. First node is the bottom line. The common ground connection is highlighted at the bottom, ties together the negative terminal of the voltage source, so that the lower ends of R2 and R3 uh, is at end and the current source. Right. So the second node left top is Vs meets the R1, and the right node the point where R1, R2, R3 and the current all are connected together. So although the circuit looks slightly complex, but systematically identifying that the junction where the elements meet, we can clearly label them as the three nodes. This identification is critical because both Kirchhoff's current law and nodal analysis depend on knowing the exact number of nodes. Here we have same circuit again, but this time let's count the branches. A branch is defined as a single element that connect one node to another node. Each voltage source and current source or resistor is connected as a branch. In this circuit, we can identify five distinct branches. Branch 1 as a VS1 connecting the bottom node to the left hand node. Branch 2 as the resistance R1 connecting left node to the top central node, and the branch 3 as resistor R2 connecting the central node to the ground. Branch 4 as resistor R3 also connecting the central node to the ground, and the branch 5 the current source IS is connecting the central node to the ground with an output V0. So in total, the circuit has 5 branches. Now let's move on to Kirchhoff's voltage law, or can be termed as KVL. The KVL states that the algebraic sum of all voltage around any closed loop in a circuit is zero. In simple terms, this means that the energy supplied by the source loop is exactly equal to the energy consumed by resistor or loads. When applying KVL, we start from a node and move around the loop. If we encounter a voltage rise first, we take it as positive. If we encounter voltage drop first, then we take it as a negative. Right? So sum of potential rise can be equal to sum of potential drop. This could be the short definition of an KVL. Right? Now let's apply KVL to the one of the loops in the circuit. Here we start at node A and assign current directions. If the I1 flows through the resistance R1, then the I2 flows through resistance R2. According to Ohm's law, the voltage drop across each resistor is given by V equal to IR. Now moving around the red loop, uh, we first rise by the voltage source Vs. Then we encounter a drop across R1, which is equal to IR into R1. Another drop across R2 will be equal to I2 into R2. By KVL, the algebraic sum is 0, so we can write that Vs minus I1 into R1 minus I2 into R2 would be equal to 0. This is how we systematically apply KVL by assigning current directions, applying Ohm's law, and then balancing the voltage rise and drop across the loop. To summarize it, Kirchhoff's current law states that the algebraic sum of current is zero as I entering a node. I mean, the junction is zero. This means that the total current flowing into a node equals to the total current flowing out. So, based on the principle of charge conversion. So, likewise for Kirchhoff's voltage law, it states that the algebraic sum of voltage around any closed loop is zero. This means that the total of all voltage rises and drop in a loop must balance. It is based on the principle of energy conversion.